So I'm going to introduce our speaker for the evening. So this is Dr. Jorge Cortes. He's an NSF MPS Ascend postdoctoral fellow at UC Santa Cruz, where he uses computational simulations to explore the phenomena associated with the high-energy universe. He received a PhD in astrophysics and astronomy from Columbia, specializing in the violent interactions of exotic stellar binaries known as spider pulsars. Born and raised in the Bay Area with roots in Michoacan, Mexico, Jorge is driven by both curiosity and community, committed to making science more inclusive. And tonight, he's going to tell us all about creatures from space. So please join me in welcoming Dr. Cortes.
Hi, good evening, everyone. Thank you, Lauren, for that introduction. So I'm here to talk to you all about spider pulsars. But I want to first start off with this image. So up here, I have this beautiful infographic from NASA, where on the horizontal axis, I have time, and on the vertical axis, I have mass. And what fills every inch of this infographic is stars. And so as a star journeys through time, to a very good degree, what dictates its end fate is how massive is it? How much mass did it start off from the get-go? So for example, for our sun, we have a relatively low mass star, and as it marches through time, its end fate will be something that's known as a white dwarf. But as you go higher and higher in mass, up to the point where you're maybe about 8 to 10 times the mass of the sun, you'll end your life as either a black hole or what's known as a neutron star. So spider pulsars are a subset of neutron stars that I will get into in a little bit. And I want to first orient ourselves. So this is an image of the Milky Way galaxy, our home. And it's full with stars, on the order of a billion, hundreds of billions of stars. And perhaps the most familiar star to us all is the sun. So the sun is what's known as a G-type star. It's a main sequence star, and I'll get into that in a little bit. And it has a surface temperature of approximately 6,000 Kelvin. So if we were to create a plot where we have surface temperature on the x-axis and luminosity on the y-axis, so as we go up in this direction, we have brighter and brighter stars. So one here is our sun, because we like to do everything relative to us, relative to our solar system. And I told you all that our sun has a surface temperature that's on the order of 6,000 Kelvin. Now we can do this exercise for a lot of the stars in the Milky Way galaxy, and after doing that, what we see is we form this diagram known as the Hertzsprung-Russell diagram. And so really the majority of the stars in the solar system, in the galaxy, fall along this diagonal known as the main sequence. As a star evolves, it can peel off of the main sequence and form these different branches. So you can get giants or supergiants. And like I said, our sun will eventually turn into a white dwarf. And white dwarfs live around here in this plot. But this talk isn't about regular stars. This talk is not about main sequence stars. This talk is about pulsars. And so where would pulsars fall on this diagram? Well, the surface temperature of a pulsar is incredibly high. And its luminosity, well, very, very dim. So it would actually fall somewhere around over here. And that's not very helpful for us. In fact, we don't really learn too much from keeping track of a neutron star's temperature or its luminosity. It's actually impossible to be able to observe neutron stars with an optical telescope. So let's learn a little bit more about pulsars. So here I have this nice little video, and maybe you recognize the San Francisco Bay Area there. And the size of a neutron star is on the order of 10 kilometers. So you have this very rapidly spinning neutron star that is about the size of the San Francisco Bay Area. It spins incredibly fast, on the order of a millisecond all the way up to 5 seconds. And another characteristic feature about pulsars is they have incredibly strong magnetic field strengths. In fact, they have magnetic field strengths that are on the order of 10 billion times stronger than the strongest magnet here on Earth. So maybe it makes more sense to classify pulsars by their spin rate. How quickly are these pulsars spinning? And so we can create here a plot that's analogous to the Hertzsprung-Russell diagram, but specifically for neutron stars. So here on the x-axis, I have the spin period, so how quickly is it spinning, and it's in log scale, so that means that 0 pertains to 10 to the 0, or 1. 1 pertains to 10 to the 1, or 10. 10 to the minus 1 is a tenth, and then a hundredth. So you're spanning millisecond all the way up to seconds. So the lower in this axis you are, the faster you're spinning. Of course, as you are spinning, you're not going to spin forever. That'd be great. But you slow down over time. And so here on the y-axis, we're keeping track of how quickly is our pulsar slowing down over time. Up here, we have what are known as magnetars. Magnetars are a special type of neutron star. They hold the crown for the highest magnetic field strengths, which are depicted here by these dashed lines, so 10 to the 15 Gauss. This clustering here that you see is a very run-of-the-mill pulsar. So pulsars are formed from supernova explosions. And so in much the same way that a figure skater will spin up as it folds its arms in a supernova explosion, you are expelling mass, but your core is also contracting. And so that naturally leads to the conservation of angular momentum. So you spin up to incredibly fast rotation rates, and all of these pulsars that are born from supernovae are clustered here. And then in a very creative fashion, we have millisecond pulsars because they have millisecond spin periods. And one of the subset of millisecond pulsars that are very close and dear to my heart, as you may have guessed from this talk, is spider pulsars. So you have these little dots that are representing what are known as black widow and redback pulsars, or a subset of spider pulsars. So spider pulsars are incredibly compact binary systems. They have orbital periods that are on the order of a day or less. So that means that they complete one full orbit in a day or less, maybe up to hours. They have very low mass companions. The only distinguishing feature between a redback or a black widow pulsar is how massive is its companion. So for redbacks, you have companion masses that are on the order of 0.2 to 0.5 solar masses. So this symbol right here is a shorthand way to say how much does this compare to the mass of our sun. Like I mentioned earlier, we love to be very self-centric, so we compare everything to, I guess rightfully so, to things that are more familiar to us. And so this symbol represents a solar mass, so for redbacks, 0.2 to 0.5 solar masses, and for black widows, you have companion masses that are on the order of a tenth of a solar mass or less, actually. In these spider pulsars, you have a very intense interaction that's occurring. So here in this animation, the pulsar is sitting at its center, and off of its poles, you have these very energetic beams. The purple here represents radio wavelengths, and the green represents the gamma rays. But in addition to these very energetic pulses, jets that are coming out, you also have this very highly magnetized ultra-relativistic wind. And that wind interacting with the companion is what's causing this material to come off of the companion. And so maybe you're wondering, why are they called spider pulsars? Why are they called black widows and redbacks? Well, in much the same way that black widow spiders consume their mates, you have pulsars consuming their companions. One of the things that is also different between redbacks and black widows is that within this interaction that's occurring, you also form what's known as an intra-binary shock. And so that's just a fancy way of saying somewhere along the distance between the two, you have a shock that forms because you have the interaction of the pulsar wind with either the companion's magnetosphere or its own stellar wind. And so in black widow pulsars, that shock forms around the companion, but then in redbacks, it's possible that the shock forms around the pulsar. So how do we observe these systems, and what can we learn from these systems? Here I have a nice diagram that's showing the electromagnetic spectrum. And on top of it, it also shows the different land and space observatories. So depending on the type of wavelength that you're trying to observe in, you'll have to either observe from the ground or have a mission launched into space to observe in space. Because, for example, in the ultraviolet, in the X-ray, and in the gamma ray, you're obscured by the ozone layer. This means that you're unable to observe in these wavelengths because if you have a ground-based observatory, you would not be able to detect anything. For radio, though, that's no issue at all. You have a lot of land-based radio observatories that are able to detect these signals. A lot of infrared observations can be done somewhere around this region. In fact, there was the Sophia airplane that was a NASA mission that had a telescope on board, and so it would go on these flights and observe in the infrared. But for spider pulsars, we're really only so far heavily relied on three main type of observations. So number one, radio. In fact, the first ever pulsar was detected using radio observations. This was by Jocelyn Bell. I forget the year, I think 1967 maybe. Don't quote me on that, I would have to look it up. But Jocelyn Bell was a graduate student at University of Cambridge in the UK. And as a graduate student, she was in charge of putting together this experiment, and she noticed something very peculiar in the data that she was taking. She noticed that there were very evenly spaced, actually precisely spaced pulses in the radio observations that she was observing, which ended up leading to the discovery of the pulsar. So a lot of pulsars are studied in radio observations. For example, the Green Bank Telescope in West Virginia. Another wavelength that you are able to study these spider pulsars are X-rays. So for example, the Chandra X-ray Observatory is able to tell you a lot of information of the type of interaction that's occurring in this shock that forms from the pulsar wind and the companion. And one of the main ways that we're able to study spiders is through Fermi gamma ray, through gamma ray observations, specifically the Fermi Gamma Ray Telescope. So I just want to very quickly go back to the animation that I had up here. One of the things that I didn't mention is that as your companion is losing mass, if you heat up a gas, it becomes ionized, it becomes a plasma. And so here you have this cloud, this enshrouding cloud that forms around the entire system. And so radio waves sitting at the lower end of the of the electromagnetic spectrum don't have a lot of energy. And in an ionized gas, radio waves have a very hard time traveling through that. In fact, as you go higher and higher up in energies, you start to have an easier and easier time traversing through ionized gas. And so even though pulsars were originally discovered in radio observations, it was soon found out that there was a lot of obscuring. There was a lot of portions of time where they expected to receive a signal, but they didn't see a signal. And so this was later found out after observing with gamma rays that you indeed had a very repeatable signal, but because of this ionized plasma that's surrounding the system as a result of the companion star losing mass over time, then gamma rays were really the main way to study these systems and actually find these systems. But we're not just limited to observations. We can also study these systems with simulations. Simulations are a great way to incorporate the physical and the analytical theories that we have and connect them to all of these wonderful observations that we have in the radio, in the X-rays, and in the gamma rays. Now, specifically, the type of simulations that I ran or I have run are what are known as particle and cell simulations. So particle and cell simulations, you can imagine you have graphing paper, and that graphing paper has a grid that goes all along the edges or all through the paper. So this grid is what we use to initialize, to set what the electric fields and the magnetic fields should be. So you can imagine I have, in an ideal case, I have this entire room that has a grid propagating through it, and all of that grid has information of what the electric fields and the magnetic fields should be at every point in space. Now I have to think about my particles, because in plasma you have to have some type of density, and the particles that are mainly in play in these systems are electrons. You have some other ions too, but for now let's just imagine that in that piece of graphing paper we decide to draw points with a pen all along it. So these points are our particles, and these particles will be influenced by what the electric and magnetic fields are at each point, and they can self-consistently move. What does that mean? That means that as they get pushed around by the electric and magnetic fields, they themselves, because they're charges, they also create a magnetic field, and they can influence the movement of their surrounding particles. And so this is a very beautiful way to not do any type of assumption of what these particles or how these particles are interacting, but very robustly understand how they move over time. And so you create this loop where you place your particles, they get pushed by the electromagnetic fields, they themselves then produce electromagnetic fields, and then you save that information onto your grid, and you continuously do that over and over again until you're satisfied or until you've run out of compute time. Now, in the models that I've ran, there is a very important ingredient. There is what's known as a striped pulsar wind. So I want to first start off with the neutron star. A neutron star will have a spin axis, and for a neutron star to be a pulsar, the spin axis has to be misaligned with the magnetic axis. So here I have magnetic field lines that are depicted here in red. And so you can imagine that if the magnetic axis was fully aligned with the spin axis, I wish I had a flashlight, but this water bottle will do. I'm spinning this water bottle, and the magnetic field is also oriented along this way. You wouldn't see anything. until I misalign the spin axis with the magnetic axis, and then all of a sudden you have this water bottle that's rotating like this. And so if you can imagine a beam of light shooting off of the water bottle, as it crosses your eyesight, you would be able to detect a flash. And so a pulsar is a misaligned neutron star spinning. Now, I also want to think about this other scenario. Let's pretend that we're on a merry-go-round and we're rotating with a certain rate. If we stand at the center, we don't really feel too much. In fact, if we were rotating incredibly fast and we were to all of a sudden stop the rotation of that merry-go-round, we probably wouldn't go flying off. But now let's imagine that we're stepping on the edge of the merry-go-round and it's rotating incredibly fast. And I were to stop it, what's going to happen? Going to fly off. And so that's what's known as tangential velocity. So even though I'm rotating at the same rate, my tangential velocity is going to increase as I move further and further along its rotation axis. So that happens here as well. For reasons that I won't really go into, there's a plasma that forms around the neutron star. Because of the very high magnetic field of a neutron star, that plasma is forced to co-rotate with the neutron star. That plasma is us sitting on the merry-go-round. The further and further you go out in radius, the more and more the rotational speed of that plasma needs to be. What is the universal speed limit? The speed of light. So you can imagine that at a certain distance, you would have to exceed the speed of light to co-rotate with the neutron star. And at that point, that's what we call the light cylinder. So all pulsars have a light cylinder radius. At that point, these closed magnetic field lines are forced to be open. All of these particles are shut out. And so beyond the light cylinder, you have what's known as the striped pulsar wind. In fact, you can imagine this because we can see it in our own solar system. And so for different reasons, but in a very analogous way, we have a striped wind that forms in our solar system. So our sun also has a rotation axis that's slightly misaligned with its magnetic axis. It's not rotating as fast as a pulsar, but it still is able to create these density waves, these striped wind, as its magnetic field interacts with the surrounding medium, all the way up to the point that's known as the heliopause. So at the heliopause, you're forcing this striped wind into each other, into an event called magnetic reconnection. There are Voyager spacecrafts that have been able to take data at these distances, and you can see the magnetic fluctuations that are occurring at these distances. So in much in the same way that this is occurring for our solar system, we also have this occur in these spider pulsars. So magnetic reconnection is this case where you have oppositely aligned magnetic field lines. And so if you imagine a rubber band, as you pull it and pull it and pull it, its tension is going to increase all the way up to a breaking point. And so magnetic field lines are almost the same way, where if you force them into tension, they're going to snap. And they're going to transfer that energy that's stored in magnetic energy or in its magnetic field. You're going to transfer that energy into kinetic energy. So you have this very nice way to tap into the magnetic field of stars or in other systems to propel things outward. In fact, you can see this from coronal mass ejections. From coronal mass ejections, you have oppositely oriented magnetic field lines, and when you push out to a certain distance, you force this to reconnect and you expel this blob of plasma outwards. And that's actually what we are able to see here as space weather. When these coronal mass ejections interact with our atmosphere, you are able to see them in these beautiful aurorae, or your satellites get disrupted. Now, specifically for spiders, what I was mainly focusing on was modeling the pulsar wind. I was really interested in modeling that striped pulsar wind that's very highly magnetized, very relativistic, and I wanted to see how that would interact with this companion. These spider pulsars are fantastic astrophysical laboratories. Not only do they make for very captivating names, but they also allow us to probe how different acceleration mechanisms can contribute to the type of emission that we see. So this is the setup that I was mainly focused on, modeling a companion star and how it interacts with a pulsar wind, specifically using what are known as particle and cell simulations. So this is a sample of one of the particle and cell simulations that I ran. Here I have a companion. I don't really label the axis, but you can ask me about that later. This is mainly used to show the interaction and how the shock forms over time. But here you have a companion. Here I have a zoomed in of that picture to really highlight the generation of these sea bubbles that we kind of saw in the heliopause animation earlier. And so this striped wind crashes into the companion. You have what's known as shock-driven magnetic reconnection. You have all of these bubbles or plasmoids form. They're able to merge with each other and they get advected in this way. And so this is what's known as the intra-binary shock. It's the location where pressure equilibrium is reached between the pulsar wind and the companion's either its wind or its magnetosphere. And you have a lot of high energy emission coming off of this location because you have particles that are getting accelerated to very high energies. One of the beautiful things about these simulations is that we're able to track all of these particles over time. We've used a lot of compute time to model these particles, and one of the luxuries of doing that is that we have information about each individual particle. So here on the x-axis, I have time. You can think about this as time, like snapshot in my simulation. And then on the y-axis, you have energy. This is gamma, and it means the Lorentz factor. But for us, let's just think about it as energy. So the higher we go up, the more energy we get. And so these simulations that I've ran, all of the particles in the pulsar wind are introduced with a set energy, with a set Lorentz factor, and that is 3. And so now, as the particles move along in time, they will get accelerated for a different number of reasons. But what's special about this subset of particles is that they all interact with this intra-binary shock at the same time, which is here. And you can see that when they interact with that shock, they shoot up in energy, and then depending on their individual history, they can either stay relatively fixed at about 100, maybe they climb up a little bit more to 400, or they can shoot up all the way to 1,000. And so it's really important to decipher what is the history of these very high energy particles? What's so special about them? Sure, they get accelerated by magnetic reconnection at the intra-binary shock, but then there's more to the story. There's more that happens that causes them to accelerate even further. And here I just want to highlight one particular particle. So we'll see here in the same way as I showed before, time in the x-axis and energy on the y-axis. And this is just showing the trajectory of an individual particle overlaid on top of this density movie. And so you'll notice that when it first interacted with this shock, it shot up in energy. But then depending on how it interacts with these bubbles or magnetic islands in the post-shock flow, it'll either lose energy or gain energy. And so this is something that's called Fermi acceleration. But you can just think about it in this way. If you have a particle that's going to have a face-on collision with a moving cloud, it's going to decelerate, it's going to lose energy. But then if you have a particle moving this way and all of a sudden you have a magnetic cloud approach it, it's going to push energy and it's going to accelerate. And you can maybe try and track this over time and see how it interacts with these blobs. And you also have a color bar here indicating the energy, and you're able to track when it loses energy and when it gains energy from these individual interactions. But you'll notice that really the maximum energy that it reaches may be 500. So really there's something more special about those particles that achieve even higher energies. So I just want to recap. So this is a very beautiful way to study spider pulsars by doing these particle and cell interaction simulations, where you have this striped pulsar wind interacting with the companion. You have this intra-binary shock that forms as a result of shock-driven magnetic reconnection, and we're really only starting to scratch the surface of what's possible with these type of simulations to help us better understand the X-ray observations, the gamma ray observations, and to really be able to apply this to other type of systems. So in spider pulsars, I mentioned that you have a very strongly magnetized wind. That's not the only location in the universe where you have very strongly magnetized outflows. In AGNs, or active galactic nuclei, you have supermassive black holes at the center of these galaxies, and you're able to see from observations jets launching off of the poles, and these jets are magnetically dominated. And in much the same way as in spider pulsars, you're able to extract that magnetic energy and funnel it into particle kinetic energy as a result of magnetic reconnection. So it becomes very important to be able to draw analogies and be able to do simulations for maybe these more compact systems that we can simulate to then apply to even bigger systems. So I just want to thank you all for your time, and I'd be happy to take any questions, and I leave you here with this bonus movie.
Questions? Yeah, go ahead.
Yeah, I was just curious about the companion. Is that just a star that happens to be close to a pulsar, and then it becomes a companion? But there could be multiple companions, I assume.
Yeah, that's a great question. Yes, so the companion is a star, and really it could be I mentioned the main sequence earlier, so it could be a main sequence star that has been messily evolved as a result of this interaction. So you're really only having maybe like the core of the sun around the pulsar. Or you can have something kind of like a white dwarf. So for a spider pulsar to be classified as a spider pulsar, it needs to have a companion mass that is less than a 0.2 solar masses. Actually, for redbacks, that range is like 0.2 to 0.5 solar masses. And then for black widows, it's about a tenth. There may be a type of configuration where you have other stars that are orbiting it, but really here we only focus on just the two. And spiders, that classification is mainly reserved for just these two interacting creatures.
So to that extent, how fast is the mass loss in these pulsars? And if it were to destroy the companion, does that mean it's no longer a spider pulsar?
Yeah, so that's a great question. So I'll maybe answer your first question first. Your second question first, and then go back to the first. Millisecond pulsars. actually, let me go back because it's nice to show this in the PP dot diagram that we were talking about earlier. So I mentioned that regular pulsars are born up here with a certain spin period. As they evolve over time, their spin increases. Sorry, their spin period increases, so that means that they slow down. Their magnetic field also decreases, that decays over time. So for millisecond pulsars, we're observing them in this regime where they have very, very high spin periods, but very low magnetic fields. So that is a clue to indicate that they probably started off as a regular pulsar. They lost some of that magnetic field, but then if there was a companion nearby, they were able to accrete mass off of it and spin up again. And so one of the leading theories for the formation of millisecond pulsars is that they're recycled. They need to accrete mass to spin up to those millisecond periods. And so in these spider pulsars, you have a very natural, very nice case, a very nice scenario where you're accreting mass potentially because of the mass loss from the companion. And so you can imagine that over time, if you erase this companion from existence, then you're just left as an isolated millisecond pulsars, which we observe a ton of. Now, when you actually go and do the calculations, the mass loss from just the pulsar wind turns out to be very, very slow, like on the order of 10 to the 9 years. So that's a gig a year. And for you to imagine that these systems contributed to the formation of isolated millisecond pulsars, it's very difficult. So it has very low mass rates.
Could a companion ever merge with a pulsar in the same way that black holes can merge? And if so, could it be measured by a gravitational wave or something along those lines?
Yeah, that's a great question. So with current facilities, we would be unable to detect the gravitational waves that that would occur from these mergings. You would, even if you're familiar with LISA interferometer, so this is going to be the next generation gravitational wave experiment that's going to be up in space, and you have like 3 equidistant satellites that are going to be measuring these fluctuations. So even that may be a little bit too much for LISA to be able to detect. If they merge, probably. You actually have these objects, which I know very little about, that are called Thorne-Shirkov objects, where you have a scenario where you engulf I think it's a red giant star, engulfed a neutron star, and so now it lives at its center. So I don't think that spider pulsars have that fate, but you can imagine that there are these systems where you have mergings, but they don't completely disrupt each other, and they somehow live in harmony in this kind of symbiosis.
Last question, but we'll be here to take more afterwards. Yeah.
The pulsar wind, is that more a physical particulate wind, or is it more energy winds that are interfering with the companion and then like just forming a cloud?
Yeah, that's a great question. It's both. So you both have electromagnetic waves that are propagating outward, but then the influence of those waves on the surrounding plasma causes it to have like regions of higher density and then lower density. So the corrugated kind of like skirt that you saw in the solar system example, that corrugation, you can imagine that every time that you see that, there's a spike in density. And yeah, so it travels not uniformly, but at the same sort of way towards the radially outward towards the companion. Yeah, so it's both.
So the particle in your simulation showed it was gaining and losing energy, but as a whole, does the wind lose energy when it crosses the companion? So
yeah, that's a great question. As a whole, your wind is gaining. So let me take a step back. you can only really conserve energy overall, right? You're not going to lose it in the sense of it's going to disappear. It's more so that you're transferring energy from the magnetic field into kinetic energy of the wind. So your kinetic energy increases, and then your magnetic energy decreases.